All right, so picking up here in video number 3 of decision making for confidence intervals versus probabilities, we are going to start with number 5. So number 5, let's read the problem. The probability that a randomly chosen Democrat supported Obama in his first run for president was 53.3%. What is the probability that in a poll of 57 Democrats, more than 30 would have supported Obama in his first run? So first of all, we're being asked for a probability, right? And this one, we're looking at, again, a percent. And when we see a percent, we are having a great indication that we're talking about a binomial random variable. So this further is indicated when we have 57 Democrats and then a number 40 or 30. So we're saying that the probability that in a sample of size 57 that by probability that the random variable, the number of Democrats, right, the number of Democrats that chose, supported Obama on his first run for president, that's our X, is greater than 30, and it is strictly greater than because it's more than. So I know my proportion of Democrats that supported him was 53.3% or 0.533. So if I want to find this probability of a binomially distributed random variable being greater than 30, and I know this information, I'm ready to go. Now, you might want the Q in here, so remember this is 1 minus 0.533. We won't need it, but if you were doing anything by hand, you might, and if you were doing a normal approximation, you might. So we have 4, 6, 7, 4, 6, 7, I believe. So 1 minus 0.533, 4, 6, 7, and so there we go. Now, to do this probability, I need to first of all say, oh, wait a minute. The calculator, the TI calculator, doesn't do greater than, right? So TI doesn't do this. So I can't do this greater than. I only can do 1 minus the probability that x of binomial is less than or equal to 30. Now remember, these are strict complements, right? If you have greater than 30, then the strict complement is less than or equal to 30. And this I can do using the binomial CDF because that's cumulative distribution and function. So this is a binomial CDF with n of 57, p of 0.533, and then my x of 30. And I'm going to do 1 minus that when it's all said and done. So 1 and then minus, and then binomial CDF is near the bottom of my second function variable, and I put in 57 for the n, and for the probability of a success, 0.533, and for the number of trials, my x is 30, and then I enter. Now, I'm always just a little bit hesitant, and so I sometimes will do my binomial probability first, and then I will subtract that value from 1 just to make sure, because I don't always get successful when I do 1 minuses. But I was successful, I get the same answer either way I do it, whether I start with this and then subtract that value from 1, or if I just plug in 1 minus the binomial. I got this value here, 4, 8, 8, 6 approximately, and Bioga seems to be consistent about rounding these to 2 decimals, it seems to me like, and at the very most at 3, so I'm not quite sure which one it was, but I'm remembering the 2 decimals. So pay attention to the round off there, and use appropriately for Bioga. My preference personally is 48.9 like this because probabilities are typically given to 3 decimals, just as it was up here. But I think Bioga is more likely to do 2. All right, now we're going to move on to problem number 6. So in problem number 6, we want to start out by reading. In a random sample of 120 Americans, 15% were found to have a hearing loss. Construct an estimate for the proportion of American population with a hearing loss using 90% confidence. Well, first of all, I see that I have 15%. Well, that seems to be indicating that I have x's, which are number with hearing loss, right? I have these x's being distributed binomially because of that 15%. So this is telling me my sample proportion is 0.15. And my n, my sample of Americans, is 120. And I want to construct an estimate for the proportion of the American population. I'm constructing a 90% confidence interval here because I want to do an estimate for the proportion of all of them. So I'm wanting to construct this estimate here, and that's done with a confidence interval. So I need to do my z-score, right? I need a critical value, and x's distributed binomially. The sampling distribution of the p-hats is distributed normally, so that means our critical value is a z. So I need to put 90% smack dab here in the middle, right, to get these negative and positive z-scores. Now you might already have those memorized for a 90%. You may already know that this z critical value that we need is 1.645 or 1.65 is usually what Bioga uses. But remember, we get this by inverse normal, and then we do point, and this 90%, right, has to be the complement what's in the both tails, and so in both of these tails we have 0.05 here and 0.05 here because there's 10% left broken into 2. So we have 0.05, and when we do the inverse normal, the second function of the variable key down to inverse normal 0.05, you'll see you get a negative 1.6448536626, and this is, remember, the minus on this side is what you got when you input this, so that's why you got the negative value here, right? Because you input that. But remember, this value is symmetric. It's the same. It's the positive value over here. And we don't really care about the sign. So now what we need is we need our proportion, our p-hat, 1.5, and we need to do plus or minus, and we're going to start out with our critical value, 1.65, and then we need the standard error. Well, the standard error is the p-hat, 0.15, times q-hat. Q-hat, remember, is equal to 1 minus 0.15 or 0.85. So that's our Q-hat. So we're going to multiply this by 0.85, and then we divide that by our n, which is 120. And that's going to give us over here our margin of error. So we're going to have 0.15 and then plus or minus, and I'm going to do what's under the radical first. So I'm going to do the square root of 0.15 times 0.85 and divided by 120, and then I'll multiply that value, which is approximately 0.032, times 1.65. and I'm going to round this value to 3 decimals, so point and 0.54, so 0.54. And now I'll do 0.15 plus 0.054 and 0.15 minus 0.054. So the plus one is what goes on this side. That is 0.204. So that was this plus this. And now I'm going to do the 0.05 minus this. So I can have the left side. And that gives me 0.096. And so there is my confidence interval. And remember, this confidence interval interpreted says that between 9.4% and 20.4% of the population has hearing loss with 90% confidence. Or we are 90% confident that somewhere between 9.4% and 20.4% of the population of Americans has hearing loss. All right, now we're going to go down and we're going to do problems 7, 8, and 9, or we're going to get as much of it as done as possible. Probably this video I'm only going to get 7 done. So next problem, 7. It says, you know nothing about the distribution of credit ratings except that the mean is 200 and the standard deviation is 20. So I only know that the mean is 200 and the standard deviation is 20. And I don't have any sample information. So I don't know that the central limit theorem applies because I don't know that there's more than 30. I have no idea. And my statistics teacher, or your statistics teacher, asks you to give the probability that a credit rating is within 1.2 standard deviations of the mean. So 1.2 standard deviations of the mean. And so we want to know probability, right? Well, how are we going to do this? Well, what is the only thing that we can use to find a probability if we don't have any more than just mean and standard deviation information, don't know enough about the sample to say, oh, I can apply normal theory? What do? Well, that's what Chebyshev is about, right? Chebyshev is going to tell us an approximate probability. So Chebyshev says 1 minus 1 over 1.2 squared percent. So it's greater than or equal to this within 1.2 standard deviations, doesn't it? So that's what we're going to find out. So 1.2, I'm going to square that, and then I'm going to take its reciprocal, and then I'm going to subtract that from 1, and that will be my answer. So this says 30.6% approximately. So at least 30.6% is within 1.2 standard deviations. So what you need to understand here is that Chebyshev works for any type of distribution. It gives an approximate probability. So if all else fails and you know nothing, you can always kind of rely on Chebyshev. The problem is with Chebyshev, of course, is this at least, right? And if you use this with normally distributed data, you'll see that it's very, very conservative. So this 30.6% is possibly a very conservative answer, but it's possibly very accurate as well. All right, in the next video, in video number 4, I believe it is now, I will go over problems 8 and 9.